Let's now get a little bit more practice dealing with average speed equations. In this example, we're asked to determine the ratio of the average speed of H2 to the average speed of O2 at a given temperature. Now, in a problem like this, sometimes it could be a little bit difficult to imagine what the problem is asking for or where to begin. And you've heard me mention before the importance of writing a mathematical expression, turning the words that the problem gives you into an equation of some sort. So if you're looking for a ratio, let's write out what that ratio or what that fraction is going to look like. We want the ratio of the U average for H2 to the U average for O2. So take the U average for the H2 and divide by the U average for the O2. Now what we can do is write the average speed equations for both the H2 and the O2. We're just going to substitute them into this equation here. So that's going to be, for the H2, we have the square root of 8RT over pi, and then m is the molar mass of the H2 here. Divided by, for the O2, you would say that's the square root of 8RT over pi times the molar mass of, in this case, O2. All right, now what we can do is begin to simplify this expression out. So by writing out the ratio like this, what we can start to recognize is that things can be simplified down pretty substantially here, because you have a lot of constants in the equation that are being divided by one another. For instance, 8 is a constant, and so when you have 8 over 8, that cancels, right? R is a constant, so R over R cancels. You're told that this is happening at a given temperature, meaning T is constant, so that cancels. And pi is a constant, and so that cancels when you have pi over pi. And that allows us to recognize the only thing that's different here is the molar mass, and so it's the only thing that's going to remain uncanceled. What we can say, therefore, is that this ratio of the average speed of H2 over the average speed of O2 will be equal to the square root of 1 over the molar mass of H2 divided by the square root of 1 over the molar mass of O2. All right, now let's kind of do a little bit of algebraic manipulation here to make this equation look a little bit nicer. So for one thing, when you have the square root of everything on the top over the square root of everything on the bottom, you could just say that's the square root of everything. So we'll just say U average for the H2 over U average for the O2 is just one big radical like this. Square root of 1 over MH2 over 1 over MO2. And then when you have 1 over something, right, like what we have in the case of 1 over MO2, then MO2 comes up to the, right, like when you put something in the denominator of a denominator, that kind of like cancels out and you bring it up to the numerator. So we'll rewrite this now to say the ratio U average of the H2 over U average of the O2 is equal to the square root of MO2 over MH2, just like that. All right, and what we notice here from this expression that we've come up with is that the ratio of the average speeds at a given temperature will be equal to the square root of the inverse of the ratio of the molar masses. And this is a result that's going to be really interesting and important for us when we continue on and talk about diffusion and effusion later on in this chapter. But we're able to kind of come up with this here, again, recognizing that this ratio of average speeds will be equal to the square root of the ratio of the inverse of the molar masses, or the reciprocal of the molar masses, like that. Now, the next thing that I can do is go ahead and plug in numbers and calculate this. And what I'll say here is that because you're taking the ratio of the molar masses, the units for molar mass cancel out. And so as long as you're consistent with the units, it does not matter whether you use grams per mole or kilograms per mole. You'll get the exact same answer. And just for the sake of being really careful with the units, every time I see a capital M, I'll just use kilograms per mole. So for O2, the molar mass is 32 grams per mole. That's what you get from the periodic table. And then in kilograms per mole, that would be 0.032 kilograms per mole. And then for H2, that's 2 grams per mole. And in kilograms per mole, when you divide by 1,000, you get 0.002 kilograms per mole. Now, because the units of mass cancel out, again, it doesn't matter what units you use. And if you used grams per mole, you'd get the exact same answer. 0.032 over 0.002 comes out to 16. And so what you're going to get is that the average speed of H2 over the average speed of O2 will be equal to the square root of 16, which is equal to 4. Meaning that at a given temperature, H2 molecules travel 4 times faster than O2 molecules. And this makes sense because H2 is so much lighter than O2, and so it should travel faster at a given temperature. As I mentioned before, this result that we came up with here, that the ratio of the average speeds will be equal to the square root of the inverse of the ratio of the molar masses, will come into play when we discuss diffusion and effusion, and that's where we're going in our next video.